Now, before we dive into the material proper, let's just take a minute and get kind of a quick overview of some linear algebra applications. I've noticed that in a lot of curricula, the way math is taught, a lot of students don't get the point of it, right? And you end up getting overwhelmed with a lot of equations and a lot of formulas and a lot of theorems and proofs, and a lot of students kind of miss why are we doing this and what is this math actually for? And I'm a big applied guy, and so what I want to do is kind of give you a sense, just sort of a potpourri of different applications, many of which you use every day, that depend critically on the linear algebra stuff that we're going to be learning in this volume. And here's a list here. This is by no means complete, and I'm just listing a few that I know a little bit about, and also are pretty surprising in some cases. So let's take the first one. So a lot of people, when they come to the computer science department at our university, I say, so what are you interested in learning about it? They say graphics. And I always say, oh, wow, yeah, I got to brush up on your math for that. And a lot of them are just blown away by that. They're like, math? Wait a minute, what? Graphics? I mean, I thought graphics was about art and color and stuff. And a lot of students sort of don't understand that fundamentally when you're playing a game, say, like let's say you're playing Mario Kart, right? If you think about something like Mario Kart, it's a three-dimensional world that you're moving around in, right? And there's little carts and a track, and you're firing these blue and green and red shells at each other, and there's people, celebrating and all that kind of stuff. All of them are moving around in this virtual realm. But you, of course, as the player, aren't seeing a 3D screen unless you have a very sophisticated console and set. You're looking at a two-dimensional screen. So every single frame of every single game that you play, every single pixel on that two-dimensional screen has to be computed. They have to figure out, the game has to know what is it going to project onto your two-dimensional screen from your perspective, where your character is in the game, in order to properly reflect what's going on in the three-dimensional world there. And that is nothing else but a big linear algebra problem. Every single time a pixel is displayed on the screen, that is computed, and we will learn and see in the application section that there's a relatively simple and elegant equation for taking a three-dimensional world and rendering it according to a particular point of view in a two-dimensional setting. And that's only one of the many graphics operations that are driven by linear algebra. The next few on this list really all stem from the fact that information in a computing system is all represented in terms of strings of ones and zeros, right? Strings of bits. Whether you're talking about a music file in an MP3, whether you're talking about an image like a JPEG or a GIF, whether you're talking about an email message, whether you're talking about a video, everything ultimately is in terms of bits to the computer, right? And when you send somebody your picture that you took on the beach or whatever, you're essentially sending them a big long string of zeros and ones, which their application on the other side knows how to interpret properly and recompose back into the composite object. Now, one of the things that we found out quickly, we as the human race, when we started using the internet, is that it would behoove us to make the size of those files as small as possible, right? Because the larger they are, the longer it takes to transmit, the longer it takes to download, and the more clogged up the internet gets with everyone trying to transmit these large files. So one application of linear algebra, one of many, is data compression, where you say, you know what, I'm sending this picture to you, but actually you don't need to send all the detail for all parts of that picture, right? Because if I look at it, really I'm looking at the faces most of all, and maybe the colors in the background and a few other details, but there's big chunks in almost any picture that are roughly just one common color, right? Or which don't have detail that are interesting to the viewer. And so JPEG and GIF and PNG and all those different formats are basically different ways of taking that long string of bits and trying to intelligently find parts of it where we can reduce the size and not transmit all the detail, which the viewer's not going to care about anyway, in order to reduce the amount of bandwidth that's going to be required on your internet connection or the amount of space on your disk, and nevertheless have reasonable quality photos. Okay. Another application similarly is error correction code. So every time you download anything from the internet, anytime you send a text, anytime you read something off your disk, for that matter, there is the possibility that every single bit that you read will be corrupted because there will be some problem in the transmission, even a momentary micro glitch that you might not even notice. Now, for some things that doesn't matter a whole lot, because if you're streaming a movie and a few frames kind of are jittery or maybe don't have all the pixels there, it's not a big deal. You just kind of quickly gloss over that or whatever. But if you're downloading something like a program that you intend to run, right? You're downloading an app to your phone, you can't afford to have one bit wrong, because if you do, then when you run that thing, it might do something very confusing or strange or even malicious to your phone. So one question is, when I get a bunch of bits that I've transmitted, is there a way I can analyze those using linear algebra in order to figure out if they were all transmitted correctly? And maybe if they were not, can we auto-correct them? Wouldn't that be cool? Then I don't even have to ask for them to be retransmitted. I can just automatically correct them to what they should have been. That seems like magic, but it is nevertheless possible through certain linear algebra operations. We'll look at Hamming codes later on in Volume 2, and we'll look at how those are used as a matrix multiplication operator, taking advantage of the null space of a particular matrix in order to guarantee that your email and that your image file and that your app are perfectly downloaded without error. Another thing related to this is cryptography. So this is obviously very big in the news, right? There's all these news stories about cyber crimes, hackers from different countries are hacking into different companies to steal information, identity theft, and all that kind of stuff. So encryption, as you probably know, is basically the science of how to take a string of data, which is information that you want to send, and encrypting it, making it into ciphertext. So basically you're taking a key and you are making a secret code out of it so that when you transmit that, the receiver and only the receiver will be able to decrypt that and find out what the information is, right? You take advantage of this every time you buy anything on the internet. You go to Amazon.com or eBay or anything else, right? And you see the little HTTPS in the upper left-hand corner of your address bar on your browser. That's the sign that what's being used right there is linear algebra code that is taking your data, running it through a sophisticated algorithm with a key such that the other side will be the only one who can get your credit card number or whatever other secret information that you're sending, right? Authentication is a related technology where you can say, I'm going to make some message and I'm going to send it to people. And I'm going to digitally sign it with a digital signature such that anybody who receives it knows that it came from me. And it's actually interesting how that can work. You can have a key that you're not letting anybody else in the world have, so no one else can sign your documents. But nevertheless, everyone else in the world can verify that you and you alone signed your documents. That, again, has to do with manipulation of vectors of bits according to the linear algebra operations that we are going to use. Modeling and simulation, so this is a huge field, and I'm not doing justice to it at all with these three examples, but there's a huge interest now in taking complex systems and trying to predict and understand how they operate. The economy is a big one, right? Trying to figure out, hey, if such and such industrial sector changes, or if interest rates rise, or if we have an inflation uptick, or if the buying preferences of certain consumers change, what is the likely impact that's going to have on an economy? And believe it or not, the way that's often done in computer programs is representing the state of the economy with a matrix of various transition probabilities, and a matrix that represents the quantities of different monetary amounts and how they're related to each other, and then being able to forecast what's likely to happen in the future through repeated applications of matrix multiplication. You can do that for population demographics, other kinds of simulations. You can do that for stock and weather prediction. How will we know what the weather is going to be like 5 days from now, given that we have certain information about how the atmospheric pressure is related in different areas of the country, and what hot and cold fronts are coming through, and how can we use those to leverage and make a prediction about how that's likely to play out in the future. All has to do with using not just scalar quantities, but vector and matrix quantities, which are the part and parcel of this class. Data mining, this is a term you may have heard, even if you don't know what it means, but again, it's something you probably run into just about every day. So, you go to Netflix and it pops up and says, hey, you might be interested in these movies, right? You might ask, how does it know to recommend those? I mean, it turns out, wow, that was spot on. I did, in fact, like the new Flash episode, or I did, in fact, like Orange is the New Black, or whatever it recommended to me, right? Well, believe it or not, it has to do with math behind the scenes. It's doing things like saying, well, given that a bunch of different users rated a bunch of different movies in a certain way, and you can represent all that in a giant matrix, how can we then make predictions about what recommendations that we don't have from certain viewers, what they will be? Is this viewer who hasn't given us a recommendation on this movie likely to like it or dislike it? Well, that depends on the people who have liked movies similar to the ones he's liked. or it depends on the properties of that movie and what other properties similar movies have, and basically it runs it through a giant optimization problem doing a singular value decomposition and other things to that matrix to be able to come back and say, Netflix predict that you, the user, are going to like these top movies. These 20 are the ones you're most likely to give a high rating to, and those are the ones that shows that to you, right? So that's completely transformed the world of e-commerce and information retrieval by using those sorts of operations, which are all based on linear algebra. Pattern recognition, another thing that you may not even realize has to do with math, but you can have a picture that you've just taken on your phone, and you can have it zoom in on the faces and find out where those are, and even, I've seen applications my kids have where it can distort the faces in funny ways. How does it do that? How does it know where the faces are as opposed to other things? Well, it has to do with the fact that it's able to run a filter through that big matrix of information representing the picture, and it's able to look for certain patterns and lock on. And we'll discuss how it does that and kind of do some fun applications where we're able to find certain parts on a picture and maybe even change them, blur the faces if we want to sort of anonymize certain individuals in a picture, for instance. Information retrieval, Google and other search engines have, of course, changed the world with how they are able to enable us to find information at our fingertips. It doesn't appear that math has anything to do with that. You type in some query like Star Wars Episode 7 Kylo Ren identity, and you get back a bunch of web pages back in its search results list, right? Well, what Google's doing, believe it or not, is it is representing every page on the internet as a vector. And we'll look at that in detail, the vector representation of a page. It doesn't seem like a page would be a mathematical operation object like a vector at all, but nevertheless, that's how Google represents it. And Google also changed the world with its PageRank algorithm, in which it basically said, let me look at all the pages and which ones have links to other pages, make a big giant thing called an adjacency matrix out of that, and then by doing algorithms and operations on that, it can predict which pages are most likely to be important, meaning lots of other pages are linking to them versus the ones it's linking to, and it can factor that into its search results list. So not only is it looking at the contents of the pages that might be relevant to your query, but it's able to say, well, these pages are probably the ones you want because they're the ones lots of people are linking to, rather than this obscure page that maybe somebody hacked together that really isn't as important in a PageRank sense. And lastly, in a similar vein, social network analysis. This is something I'm doing some research on recently, where we're able to take a social network, something like Facebook or Twitter, where you've got a lot of different people with relationships. They are friendships in Facebook, or they are following relationships in Twitter, and we're able to analyze that graph and say, if we wanted to sow a rumor in this social network, and we wanted that to reach the maximum number of people, who would be the users who would be the best disseminators of that information? It has to do with taking that big giant graph, which is essentially all the different users and their connections, and then representing it as a matrix, which we can then find the eigenspectrum of and learn a lot of very, very interesting things about which nodes are most important, where we can break down the nodes. Can we discern that there are sort of two different cliquish subgroups in the graph where they have a lot of connections between them, but not very many connections to other clicks in the graph? Are we able to determine, for instance, the political climate in the United States right now? Can we see that it is, in fact, polarized? And can we find ways to get people from different points of view politically to have more connections to each other so that there is a more fertile cross-pollinated conversation going on? All those things are possible to get your handle on once you have the tools of linear algebra at your disposal and you are able to use those in your analysis. All right, so just sort of a sweeping overview of some of the cool stuff, and I want you to understand that every single thing that we learn mathematically in this volume 2 is going to have direct applications to things and technologies that you use every day. All right, I'm excited to get started. I will see you in episode 2 when we begin diving into the math whole hog. Until then, take care. See you next time on All the Math.